What we're going to begin going through here are some concepts regarding perpendicular bisectors and angle bisectors. Okay? The first thing is to go through some definitions here. So a perpendicular bisector is exactly what it says, okay? And it's abbreviated with a symbol for perpendicular and then the abbreviation for bisect. And a perpendicular bisector is an element that is perpendicular to and bisects a segment. So you can see from the labels right here, it's perpendicular to and it bisects. And so again, the definition is built into the word itself. And the perpendicular bisector theorem says that if you take any point on a perpendicular bisector of a segment, that point is equidistant from the endpoints of the segment. Okay, so any point on a perpendicular bisector of a given segment is equidistant from the endpoints of that segment. And so here's what that's saying, and this is kind of building up to what happens in an isosceles triangle. But if you have this perpendicular bisector, so CP is the perpendicular bisector of AB. That means it's perpendicular to it and it bisects it. And therefore, any point that's on that perpendicular bisector, like C, is equidistant from the endpoints. So the conclusion you can draw from that would be that AC and BC are equal. And now this would extend to any other point on this. So if I took this point right here and connected it to each of these endpoints, notice I'm using 3 tick marks. So this is not the same distance as AC here, but also if we took that, you would have equal sides or equal lengths for any point that lies on that perpendicular bisector. Right, and then the converse to this means you switch the hypothesis and conclusion, and that is if you have any point that's equidistant from the endpoints of a segment. So here if we see that point D is the same distance from A as it is from B, that means that it will lie on the perpendicular bisector of that segment AB. Okay, so we're just changing the if and thens. So any point that is equidistant from the endpoints of a segment lies on the perpendicular bisector of that segment. And so what that would mean is that if AD and BD are equal to each other, then D lies on the perpendicular bisector of AB. All right, now this is going to be used later when you have an isosceles triangle where you have those the point are equidistant from the endpoints of this segment. It just is telling you that that perpendicular drawn straight down is going to bisect the base. Okay, so any perpendicular height or altitude that you draw from the vertex of an isosceles triangle is always going to be the perpendicular bisector of that. Okay, and so that's basically what you're going to be asked to find for this. So if we take a look at this question right here first. Okay, so given triangle ABC with perpendicular bisector AD, so that means again we see perpendicular and bisect. What do you know about those two side lengths? AC and AB are equal. So there's the conclusion you can draw. And then I want you to take this conclusion now and see if you can solve it algebraically. Find what x is. Notice it's asking you for the distance AB, so remember that. You're not just finding the variable, you're going to plug that in. But see if you can find what's the distance AB given that relationship. Remember, oftentimes it's helpful if you know you're finding an expression that you need to evaluate, because you can enter your answer as a calculation. Go ahead and enter the sort of overall calculation you're going to use. AB is represented by 6x minus 11. So if I leave it as 6 times some placeholder minus 11, I need to solve for x. And so I'm going to take the expressions for AC and AB, plug those in, 9x minus 32 and 6x minus 11. Those have to be equal. So if I do the math for this, move my x's to one side, move my constants to the other, I get 3x, bless you, is equal to 21. Divide by 3 to solve for x, and I get x is equal to 7. And therefore, if I plug that back into my answer, I get my calculated value. Remember, you can enter your answer as this calculation. If you do that, you'll see a little preview of the solution over here. 6 times 7 is 42. 42 minus 11 is 31. And so you can also enter the exact answer of 31. All right. This next question is the one that's going to be a challenging question, okay, the harder of the questions that you're going to see here. Okay, so this is going to this question here is going to incorporate multiple concepts, okay, and so that's what's going to make it tough. So let's kind of break down and see what we have to solve for in order to answer this question. Okay, so you're given the equation of, or you want to find the equation of a perpendicular bisector, okay, given two endpoints. So if you think about what this is going to look like, I'm just going to sketch it here, not necessarily to scale, but in the right quadrants. So I have one endpoint at 10, -1, so that's going to be somewhere around here. And the other one is -12, 11, so that's going to be somewhere up here. Okay, so what I want to do is, what I'm looking for here is I'm going to find the perpendicular bisector of this line. Well, I first need to know the bisector, and then I need to be able to use that to create a perpendicular. And so based on conceptually, what is it that you need to find? What is the bisector called of a segment? It's called the midpoint. Okay, you guys have a calculation for finding the midpoint of midpoint of an ordered pair, okay, on a coordinate plane. And if you recall, that formula for this is that the midpoint is going to be a series of calculations. First calculation is the x-coordinate. It's the average of the two x's, so x1 plus x2 over 2. And the y-coordinate of your midpoint is going to be the average of the two given y, so y1 plus y2 divided by 2. So first thing I want you to do is see if you can calculate the midpoint given these two endpoints, 10, -1, and -12, 11. Right, so you see I've labeled my two endpoints as x1, y1, and x2, y2, again, just to give a visual reference point. And so if I take the average of the x's, I have a -12 plus 10 over 2, and I take the average of the corresponding y's, 11 plus a -1 over 2. And if I simplify what I have, that gives me -2 over 2 for my x-coordinate and a 10 over 2 for my y-coordinate, which I continue to simplify, and I get -1 and 5. So there's the coordinates of my midpoint. So that's the first step. All right. The next step is we need to create an equation for this line. Well, we found what one point is. Okay, so this point here is going to be -1, 5. Now, what else do we need to write the equation of a line? We have a point. We need the slope. Okay, so what we're next going to have to do is identify the slope. And the slope that we're going to look for is the slope of the original line, or a line segment. Okay, so the slope equation, if you recall again, is the difference of y's over the difference of corresponding x's. So there is our slope equation. So remember, we're finding the slope of the original line. So we're going to use the two given points, y1 of 11 minus y2 of negative 1, and divide by the x coordinates, negative 12, minus the x coordinate here, 10. So if we continue to simplify what we're looking at here, minus a minus gives me a plus, so I have 12 in the numerator over negative 22. And again, if I simplify what I'm dealing with here, I will always move the negatives up top, and I can cancel a factor of 2 from each of these. So a negative 6, again, we take a 2 out of that, take a 2 out of this, we get negative 6 over 11. So there is our slope. That's our second step. So that's the slope of that original line, but we don't want the slope of the original line, we want the slope of the perpendicular. Do you guys remember how to calculate the slope of a perpendicular line? You do what? So it's the flip, we flip the fraction and we subtract, or we put a negative in front, right? So it's the negative reciprocal. So here, if we take and find our next step, find the slope of the perpendicular. That slope of the perpendicular is the opposite sign, so it's going to be positive. Flip our fraction, 11 over 6. So that's our third step. Once we have these three steps, we're now ready to create our answer. Now, you guys have 3 different forms you can write an equation of a line. Okay, the easiest form to use, especially if you're given a point and a slope, is one that you guys probably rarely use. You don't think about it. Most of the time students start or think that they should use y equals mx plus b, which is fine. It'll give you the right answer if you calculate all of that. But the point slope form is a lot more direct way to enter your answer. So if we look at this step 4 as write the equation, point slope form is this: y minus y1 equals m times x minus x1. And the information you need for point slope is the coordinates of one point, x1, y1, and the coordinates of the slope, m. You have those. Here's x, y, and slope. You have the 3 things that you need. And so the easiest way to answer this question is to just take this form, y minus our y coordinate, which we found of our midpoint 5, equals our slope, which we found is 11 over 6, times x minus our x coordinate of the midpoint, negative 1, so minus a negative 1. And that would give us our answer right here. You don't need to put it into slope-intercept form. You can leave it in this form. Now, if you wanted to, you could distribute the 11/6, add 5 to both sides of the equation and write it in slope-intercept form. That's acceptable, but it's not necessary. And if you can use this point slope form, it eliminates one more step, and it's a step that involves fractions, and so students do tend to make mistakes more with fractions than they do with integers. And so I recommend just using that form. All right, so you guys can see that this is a more complex problem, like one of the more complicated type of problems that you guys have seen. And just make sure that you can follow those steps when you are writing your equations. All right. There's one last problem, and that last problem has to do with angle bisectors and the relationships that are created there. So let's look at how this fits in with definitions first, and then we'll go through that question. All right, so first, an angle bisector. An angle bisector is defined as a ray that cuts an angle into 2 congruent angles. Okay, and so here, the angle bisector that we're looking at is ray YW. And if ray YW is an angle bisector, that means that these 2 angles are the same. And so the conclusion would be that angle XYW is congruent to angle ZYW. So that's the conclusion that's drawn by definition of angle bisector. Okay, now, the angle bisector theorem is kind of similar to what we saw with the perpendicular bisector theorem. And that is, if you choose any point on the angle bisector, is going to be equidistant from the sides of the angle. Now, it doesn't matter where you work on this. When you find the distance from a point to a line, right, it's always going to be a perpendicular distance. So here, what we would see is that if ray AD is an angle bisector, meaning those two angles are the same, then that means that the distance from point D to either of these lines is going to be the same as well. So the conclusion that you would draw from this would be that BD is equal to CD. Those are the same measures. Okay, and that will be true for all different, like if you picked a point right here on the angle bisector and found the distance to this, the sides of this angle, these two distances here, using 3 tick marks, would also be the same. Okay, and so the converse of that should make the same sense, the same kind of argument from the previous one, and that is if you have a point that is equidistant from two sides of an angle, then it's going to fall on the angle bisector. And so here, if point D is the same distance from B as it is from C, we see that it's perpendicular. Okay, that's the distance. Then the conclusion that you can draw is that if BD is equal to CD, then that means that ray AD is the angle bisector. Okay, but for the most part, what you're probably going to be using for the calculations on this is this second box, okay, the angle bisector theorem, which will be that those two distances are the same. Okay, so see if you can find distance BC in this example, this third example here from this section. So first of all, remember CB and BC represent the same distance, right? It's just the distance between points B and C, or C and B. So there is our expression, 12 times some unknown x minus 77. So again, to help me, remind me that I'm not just solving for x on this problem, I'm going to take x, evaluate an expression using whatever x is equal to. And so the relationship is that if AC bisects, I know that these are equal angles here, angle AB or BAD, then that means that these two distances have to be the same because point C lies on that angle bisector, therefore it's equidistant from the two sides. And that gives me the relationship that 12x minus 77 has to be equivalent to 5x. Okay, and now I can solve this, move all my terms, or all my variable terms to one side. Since it's just a one-step process, I'm going to move the x's over. Even though I'm dealing with a negative here, that's still fine. It just eliminates the movement of one of those terms. And when I divide by -7, the negatives cancel. 7 into 77 leaves 11. So again, my answer is not 11. That's what x is. I plug that in, and when I evaluate it, I would get my overall value here to be 55. And that would be my solution, either of those forms.